In this video, we'll work on how to use your copy of the virtual machine with some of the Synopsys tools for IC design and simulation. Let's start with running the Oracle VirtualBox and starting Lenny, the 64-bit version of the virtual machine. Once Lenny is being started, we can then discuss on how we'll continue with this tutorial. We'll begin with a simple verification of an existing NAND gate design. Then we'll test the schematics of the design using Synopsys HSpice using a precompiled testbench. Then we finally test the existing layout using the Synopsys tool called Hercules for design rule check and layout versus schematic compare. We then use layout parasitic extraction tool, the StarRC, to see the parasitics that are being formed because of our layout. We'll begin by entering the password of the CentOS environment, then pressing on login. We can then right click on the desktop and click open in terminal. This will open the command prompt of the CentOS environment, and we will then go to the home directory, which is this one. You can also use cd command to directly go to the home directory. Once you're in the home directory, we'll use Custom Designer to start checking on the schematics of the design. You can click on this library manager, or you can go to tools, then library manager. Here in the library manager, we'll open this project. This is our example project, and let's use the NAND gate as an example, and we'll see the schematics. As you can see, this is the schematic of a very simple NAND gate. We have two PMOS devices up top and two NMOS devices below. They each have inputs A and B distributed to one of each, and this is the output section. Now let's see the test bench that has been prepared already. As you can see, there we have made a symbol for that NAND gate, and we have two pulse inputs and a output capacitor of 10F and a output voltage DC. You can see the symbol here. It was created. It's a very simple NAND gate symbol. So now let us proceed to simulating this circuit using the SAE. Here we can add the models. This is very important because the models directory is in Synopsys, and models HSpice. And for this example, let's use the RF18 library and the TT section. Then we add the analysis options. Let's add a time step of 1 femto and a stop time of around 320 nano. Let's add outputs for input A, input B, and the output. Then let's save this by pressing S, pressing OK, and begin the netlist and run operation. Just press OK. HSpice will begin running and simulating the schematic diagram of the test bench, and it will open. Just ignore this error for the moment. It will begin to open the custom wave view. press Control H plus O to open both the file view and the open file. Open the HSpice.tro, then expand these nodes because we include the outputs A, B, and the output itself. We can finally see here the operation of the NAND gate. Change the zoom to this one and finally zoom in. You can see the normal operation of a NAND gate. However, this is not a very good example because there are lots of huge glitches. This is not the point of the video. You can then close this, having verified that our test bench is okay and thus our schematic is fine. Let's proceed to the layout. Our first job in layout after finishing our basic layout is to verify the design rule if our layout follows the design rule of the technology we're currently using. So let us go to setup and run. You should know now that we need to create a run set. The run set is still found in the Synopsys folder and then in Hercules and then in DRC. As you can see, we're using the 18 micrometer technology from TSMC. We'll open this, we'll select that. As you can see here in the control variables, they are automatically populated, and also custom options, we see a blank space there. Just leave that by default and you can begin pressing OK to initiate the DRC run. DRC will then activate and begin checking your layout for design rule violations. As you can see, we have some violations. Few of them are all for area coverage. As for now, we can ignore these types of errors. So this means that our layout is fine. We can make an error, however, by adding intentionally in an error in our design. For example, we can add a metal 1 here. It will most likely cause an error. We'll do verification and run because we have already set up it in our first run. As you can see in the DRC errors, we have produced a few more errors here. And as you can see, it has highlighted the area where the error may have occurred. This area is that one, which we recently added. So our goal here in the DRC check is to delete these errors if they ever occur. Now that's deleted. We'll go back to verification and DRC and run it again. We find that we have eliminated the errors. These errors, we can ignore them, they are by default. Next is we run the LVS, or the layout versus schematic. This actually uses the Hercules program just like the DRC. So we need to set up Hercules and we'll open the run set. It's in Synopsys, Hercules, LVS, and this one. As you can see in the net listing options, it has added this part. We need to delete this because that will cause some errors later. As you can see here, the control variables are immediately populated. Here in the custom options, we must find the layer map. The layer map is still in the Synopsys folder. TSMC 18RF and all files, we can find layer map here. By pressing OK, we will begin the LVS operation. You may press this view output to see the operation while it is doing its job. As you can see here, the LVS is working and it's done. As you can see, the compare results are doing great. However, there are some extraction errors. However, we can ignore that for a while. The important part is that we are having a clean result. The load result here this is the important thing here, clean. Next goal is to run the layout parasitic extraction using StarRC. Let's set it up and run, and let's open the run set. Same address, blue Synopsys Hercules StarRC, and let's use StarCMD. And the extraction options, we need to use RC here, and open the next grid file, this one, and make sure this one is the name of your cell.hercules.lvs, then Milky Way output, and click select. Don't go to XTR, just here, then click select. In the output options, as you can see, this is one that you can configure manually by yourself. Make sure the output run set is by default this one, and the format is SPF. Netlist file, you can decide where you want to place your output. I want to place my output in the name of the library, the cell, and I would make a new folder called StarRC and name it output.sp. Just click yes, and here in the custom options it's blank. After finishing this configuration, click on OK. However, before we do this, you must note that we need to run a new LVS using RCDEC. So for the moment, we'll only click cancel. We'll rerun LVS using setup and run, and this time the controlled variables will use RCDEC. Click OK to run LVS using RCDEC. As you can see, Hercules is done. Just close this, and note that Hercules VUE or Hercules View did not show up this time to show that our layout is clean because we're using RCDEC. However, we'll use setup and run, verify that our options are correct, and press OK. It will immediately run a StarRC. Once you find this extract pp parts, that shows that your StarRC is done. You may now close this. Then go back to the terminal and find your StarRC simulation. Let's go back to the terminal and go to CD. Let's click ls and let's find that folder. Place that file in ECU195. Use Ctrl-Shift-C to copy anything, and use Ctrl-Shift-V to paste. Inside here, we go to L2 NAND 2, and as you can see, we have the StarRC directory, and we have the output.sp. We'll edit that output using gedit and change all the occurrences of n into nch. and make sure you match the case and match entire word only. Do not forget these two. Then click replace all, and also change P to PCH. Make sure to check match case and match entire word only, and replace all. As you can see, just found and replaced 9 occurrences of that text. And close this. You can now save this output.sp file. Next, we'll find our simulation of the test bench. What will we be doing here is to resimulate our test bench, but this time using the StarRC output library. So we'll find our test bench simulation from before in the CD simulation in L. Then as you can see, we have our libraries here. We'll open EC195, and inside here we have L2 NAND, L2 NAND, nominal, and we can find that we have the results and netlist. Go to the netlist part, and here we can find the input.spi. We'll copy that input.spi using the command cp and paste it in the home directory, the project ECE195, and L2 NAND StarRC. Now we have two files in this directory, the output and the input. Let's go to that directory and ls. As you can see, we need to edit now the input.spi using gedit. We have a new tab here, which is the input.spi. This is the entire simulation of our test bench that we simulated earlier. We will need to replace this. We will delete that, and we will also delete this part. Those are comments, they are not necessary. However, we need to add this as a include. So next we'll use the .include command and just type output.sp. We have included the file output.sp to this HSpice document. Then here, as you can see, it has instantiated the one that we deleted. We will instantiate this output instead. Let's copy this subcircuit definition, copy or Control C, and pasting it here in the X part. Make sure this one remains. Just paste it here, and make sure you put the instance name in the last part. As you can see here, we have out and B, A, the VDD, and the ground for L2 NAND 2. Just click save, and now we can simulate input.spi by using HSpice. Input.spi. HSpice is now beginning simulation. As you can see, job has concluded successfully. Use the ls command to see what the files were produced. As you can see, we have input.tro, that is the transient analysis, and just use wave view to show that output. As you can see, we have opened the wave view successfully, showing the A, B, and C outputs. We can then compare that to our original simulation in the simulations directory. You see 195, L2 NAND 2, schematic, HSpice, nominal, results in simulations. We now have two waves to compare. We'll just need the output part. Then we can see here the difference between the two. If we combine them both, we can see where they differ from each other, which is better, and what needs to be done to correct inaccuracies. So thank you for watching. We have successfully gone through all the phases of the simulation. We have run the HSpice simulation, both the LVS and DRC supported by Hercules, and the LPE layout parasitic extraction supported by StarRC. This is all for the first video release of this series. Thank you for watching.